All right, next up, we're going to go into cell notation, sometimes also called cell schematics. So you can see this picture on the left here, the picture I've previously drawn. It's a pain to draw this. So we need a better way to communicate all of this information. And so that's through these cell notations. And the cell notations always go from the anode to the cathode because we follow the flow of the electron. And the electron travels from the anode where oxidation is occurring to the cathode where reduction is occurring. So let's take a look at this. If we think about what kind of electrode here, we have a solid copper electrode. So we'll say CuS. And then we'll draw a straight line. The straight line represents a phase or a separation from phase. So single line separates phase, right? Most of the time, this will be the solid electrode and the aqueous solution. And so what's up next is our solution. In this case, it's 1 molar of copper nitrate. So you have to state the concentration, 1 molar copper nitrate, and it's aqueous. And then we do a double line. The double line represents the separation of the half cells or the salt bridge. And then we go into the cathode. On the cathode side of things, first off, we have our solution, our 1 molar silver nitrate. Aqueous, and then a single line to separate the phase. And then here we have a solid silver electrode, right? And so it makes sense. If you think about the flow of the electron, it's going to go from left to right. It's going to leave the solid copper to become copper 2+, and then it's going to go across and interact with the silver plus to form silver solid. So one thing you may have noticed is that the cathode electrode will slowly disappear, right? Because it's going from the solid into this aqueous solution, while the cathode electrode will not disappear. In fact, it'll actually grow because some solid is being formed on it. And so what that kind of means is that we don't necessarily have to have a cathode that is made out of the same material as the solution. So let's take a look at that. So what if you had a galvanic cell with a platinum electrode on the cathode side? And I give you this reaction. We'll say magnesium as a solid plus 2 iron 3 pluses forms magnesium 2 plus 2 iron 2 pluses. So think about what's going on in oxidation and reduction. The thing that is being oxidized is the magnesium. It's going from magnesium 0 to magnesium 2 plus. And thus releasing these 2 electrons. If we think about what's going on the reduction side of things, 2 of these iron 3 pluses are then scooping up these 2 electrons and forming 2 iron 2 pluses. So you see here, we're not forming a solid. That's still okay. So if I told you the solution was 0.1 molar magnesium chloride and 0.2 molar iron 3 chloride and 0.3 molar iron 2 chloride, how would you draw this cell schematic? Remember, you want to go follow the electrons. So go from left to right, anode to cathode, oxidation to reduction. So all the way on the left, we had solid magnesium, followed by a straight line to separate our phase, our aqueous solution of magnesium chloride, that is 0.1 molar, a double line to separate the 2 half cells, and then we have a solution that is 0.2 molar FeCl3 and 0.3 molar FeCl2. So to separate the 2, we just use a comma because they're mixed in solutions. No straight line, they're still in the same phase. and then a straight line for our solid platinum electrode. In this case, we don't have a iron electrode. We have a platinum electrode. So let's take a look at what that cell would actually look like. Right, and according to our cell notation, this is exactly what our cell would look like. Notice on the left, we do have this electrode is actually interacting, right? The electrode is made out of magnesium. That magnesium is dissolving because it's forming magnesium 2+. So this is what's called an active electrode. And it's made of one of our redox couples. Right, so either the magnesium or the iron, in this case the magnesium. And then on this other side, we have this platinum electrode. We don't see platinum anywhere in our redox couple, right? It's not being oxidized, it's not being reduced, so we don't see it there. So it's what's known as an inert electrode. Inert means it doesn't react. Right, it's just there to help transport these electrons. Cool. So given this info, you should be able to draw cell schematics or read cell schematics.